12.5 that you want to look at? 12.5 or 12.4?
Did we finish 12.5?
I think so.
I thought we had one more.
You might have one left.
Haley, did we do this one?
We didn't do the last problem.
Okay.
We did problem 6 from 12.4.
We did?
Could we?
Oh, could we? Absolutely, we
Just
can.
part B.
Yeah, 6 from 12.4?
Yeah.
Absolutely.
It's just partials.
Finding partials.
6.
6 from 12.4.
I struggled a little bit with the kind of the 4 partial derivatives of 4u over v plus 6w. And finding f and g was a little weird. I had a hard time isolating what's what.
Is that the one over? I don't think it's
Is that?
I think it's 7. Is it 7?
Yeah, we can take a look at that. And this was 12.4. Did we say it was 4 or 7?
12.4, number 6.
Number 6. Neither. Okay.
Almost.
Number 6. Okay, so first partials, which one is the one you want to find?
So it was, let's see if that's the same. Yeah, so it was f of v.
F sub v.
F sub
So we want to make sure we say sub v because f of v means function of v where v is the independent variable. So we want to say f sub v. F sub v. So first off, it's in a quotient, so we have to use the quotient rule. So we're going to go low partial high with respect to v, which is 0, minus high partial low with respect to v over denominator squared. So this part all goes away. And we're left with minus 42 u divided by 6v plus w quantity squared. That make sense?
Yeah, totally.
Yep. Cool. Any other questions on that? Make sense?
And then we just kind of continue on for the u and w.
So how about f sub w? What, let's do f sub u first. How about f sub u?
It's going to be 7 over the denominator.
V and w are constant with respect to that, so we just end up with 7 over 6v plus w. Right? V and w are constant. And then when we partial f with respect to w, it's going to look a lot like the first one. We'll use quotient rule, and then we have a multiplier of 1 instead of 6. Yeah. And then, Samantha, do we think it was 7?
Well, it said 12.4.75.
So we know
I think
it's-
it might have been.
I know it's in 12.4 for sure. Getting there. One more?
Oh.
That one. Okay, so here we have some crazy looking stuff. And we want to do we want to take the partials. We have two resistors in electrical circuit, R1 and R2, wired in parallel. And we want to find the partial of R with respect to R1 by solving for R and differentiating. So let's see if we can do that. Okay, so first off, we don't have R written as a function of R1 and R2. We have R in the denominator. So we don't have R written as a classic dependent variable. We don't have it as R equals. So first thing we have to do is remedy that. So we're going to have R2 plus R1 over R1, R2. So we get our common denominator, write it like that, and then we can take the reciprocal of both sides. Once we have it written as a proportion, then we're allowed to flip it. I'm going to write it as R1 plus R2 in the denominator. So now we have r written as a function of r1 and r2. And once r is written as a function of r1 and r2, then we can partially differentiate it with respect to either one. So we could write it this way, or we could write it this way. Doesn't matter. So r sub r1 or partial r with respect to r1. So quotient. So we're going to do low partial numerator with respect to r1. And what's that? r2. Low d high minus high d low. So now partial, so we did low partial high minus high partial low with respect to r1. And what's that? 1. And then over the denominator squared. And then we're going to get some cancellation. And we're going to end up with r2 squared over this. And I think that's everything, right? Because that r1, r2 will cancel with that. And then we have r, yeah, so we end up with that. Make sense? You got it right. Cool. Any other ones you want to look at? Does that make sense?
I did all of this except I just didn't see how to get from here to there.
This
Like,
one to this one?
I didn't see how it was canceled.
Do you see it now?
No.
Oh.
This is like what I had written.
So the step I skipped is one you want to see?
Yeah. I got to that and then so I knew like that was the answer, but I couldn't see how I got
Yeah,
there.
so if you distribute this R2, I think you'll see it. So we're going to take that R2 and distribute it. And then over here, the multiplier is just 1. So then we have positive and negative. Do you see it now? So this guy, so these guys, positive R1, R2, negative R1, R2, so those go to 0, and then we just have that one term left.
We do 13 or 14? Those are a little harder.
Can we just do all of them?
Let's see. Let's look at 13 or 14. Oh, look, I'm getting hoodwinked here. Let's see what 14 looks like. Oh, that one's easy. Joking.
She's like, no.
All right, so, yeah.
I don't even know, like, my perspective on how hard or easy it is.
Whoops.
Not there right now. I don't know anymore.
I think some of them that are easy take a long time. Some that are hard. I don't know, it's hard to tell whether they're easy or hard. Okay, so this one here, we're talking about this wave equation here, this one-dimensional wave equation. We're trying to figure out, we want to show that this function satisfies that. So I won't do the whole thing, but I'll point you in the right direction for sure. Oh, and let's just be clear that u is a function of x and t, which looks a little weird because usually it's x and y or s and t, but so we just have an x and a t. So it's a two-variable function, and if we want to figure this out, over here on the left, this means the second derivative of u with respect to t. So I want to point out one thing with notation, which we haven't really talked about carefully yet. So u sub t is the same thing as the partial of u with respect to t. And from there, we can partially differentiate again. So we could then go to u sub tt, which is going to be this. That will be the second partial of u with respect to t. So those two notations are the same. The thing that is goofy is this. So now, when we have u sub t is the partial with respect to t. That's a function of two variables still. It's got t's and x's in it. So when we partial that thing, we have t's and x's still. If we were to do this, here is the part that can get very confusing when you look at mixed partials. So when we use the subscript notation, we keep adding the next partial to the right. That is different with the differential notation. So if I now want to partial this with respect to x, it's going to look like this. So we are doing a second order partial, so the numerator gets the square thingy, but we're going to do this order. So with differential notation, it's going to the left in the denominator. With subscript notation, it's going to the right. So here, this says take u sub t and then partial it with respect to x. This says take partial of u with respect to t and then partial that with respect to x. So the order is different whether you're using differential or subscript notation. So that's one thing to keep in mind. We're not dealing a lot with second order mixed partials, definitely not with the wave equation, so it's not a big deal here, but just as an FYI, beware that those subscripts are different. And it's because the idea with this one is that you're taking the partial with respect to x of the partial of u with respect to t. So when we take the partial of something, we're applying this operator, and that operator it's got the x on the outside. We're going to partial with respect to x. It's on the outside, so it stays on the left. Whereas with the subscript, the shorthand notation, we just keep tacking on the direction that we're going. We're going from left to right instead of the other way, instead of from right to left. Okay, so with this wave equation, we've got a second order partial of u with respect to t and a second order partial of u with respect to x. And this is the simplified wave equation. If you're dealing with more than one dimension, the thing looks crazy and it's more difficult, and you'll see it in some crazy classes later on. But in the one variable, in the one-dimensional case where you're talking about a wave going down a wire or a string or something, it all boils down to this, where there's no mixed partials. It's just double partial with respect to t, double partial with respect to x. So it's a little easier. So let's talk about taking the partial of this with respect to t first. So we'll do one of these partials, and then I'll set you on your merry way. We can revisit it if this isn't enough. So if we're going to partial that expression with respect to t, we've got a t inside there, we've got a t inside there, so we're going to just come left to right. The partial of a cosine is a minus sign. And then the partial of the inside here, what's the partial of the inside with respect to t?
C.
5c.
Oh yeah,
5c? Because that
X is constant.
because that x is constant with respect to c, but that with respect to t, I mean, t's and c's. With respect to t, it's constant, but that 5 distributes so that this is really on the inside. We have 5x plus 5c times t. So the partial of the inside with respect to t is 5c. So we're going to end up with minus 15c. Oh, I guess I don't need to make it as a fraction. So we're going to get minus 15c. So that's the partial of the inside, and then sine, oh boy, of 5x plus ct. I'm just going to write it like that. And then we differentiate sine, so that's going to be a cosine. And let's see, the partial of the inside with respect to t, negative c, so we're going to get negative 4c times cosine of x minus ct. So that'll be our first partial of u with respect to t. And then if we want to partial that, I know, right? And then we do it again. Do it again with respect to t, so then we can get our second order partial. So do the same thing again. Partial of the inside here with respect to t is 5c, so we're going to get a 75 on the outside, and I'll let you try the next one on your own.
It would still be negative though, right?
Well, we're going to multiply this by 5c. It's going to remain negative because partial of sine is cosine. Yes, you're
But
right.
the second one went
The second one is going to stay negative also.
Oh, because the when
Because partial of that's a negative sign, but the partial of that's a negative c, so 3 negatives is a negative. 3 negatives is a negative. Yeah. All right. Any other delay tactics?
Unfortunately, no.
Unfortunately, no. Good. This is so cool, the stuff we're about to do. So this is what you've all been waiting for. The derivative in any direction.
This is great. Oh, great.
Partial derivatives
Nice.
are like only 2 of the possible directions. We want to find the rate of change in every direction. Yes, we do. Yes, we do.
Is that like a royal we?
Yes. It's a royal we. Capital W. We have been waiting for this. Okay. So you're imagining your surface. And you're imagining a plane perpendicular to the xy plane intersecting your surface. So when you've got this vertical plane, it intersects your surface at a curve right there. And let's figure out what's going on here. So that plane is lined up with a particular direction down in the xy plane. So in the domain, we imagine ourselves standing down in the domain and we say, hey, okay, I see that surface up there. I want to know the rate of change in that direction. So we create a unit vector in the direction of interest. And that unit vector then gets turned into a line. We then think, oh, okay, well, let's take that unit vector and let's build a line through that unit vector. And then if we project that up onto the surface, ooh, that's the curve that sits on top of that purple line. So we have this curve in the surface, and the rate of change in that direction is going to be whatever the slope of the tangent line is to that curve. So that's what we're trying to find. We are now saying, okay, well, now let's imagine us standing on the surface. If we look through the surface, we're going to be walking on top of this purple line, and we're going to be walking this direction because that's the direction we want the rate of change. So we're imagining looking down, seeing this unit vector down there, and we want to know what's the slope in that direction. What's the rate of change if we were to walk in that direction right above that unit vector?
Is that a function? Like for each point along the curve? Is
We
that
are going to
different?
create a function.
Okay.
So that surface, what we're going to create, this is just a curve. And a curve we should be able to describe with one variable. So what we're going to do is figure out a way to replace the x and the y in this surface with just one variable so that we can then take its derivative. That'll be the idea. All right, so first let's analyze this vector in the xy plane. Down in the xy plane, this direction vector, the direction that we want to know the rate of change in, we create this following line. The way we create the line is to figure out what the slope of that vector is, and we're going to do that. So we're going to add a little bit to we're going to start at a comma b. We're going to add a little bit to a and add a little bit to b, but we're going to add that little bit in a prescribed way. We're going to know what the slope of that vector is, and so then as we use h as being the multiplier in here. So just like the h that you're used to in the limit formula for the derivative, x plus h. So, and when we did our partial derivatives, we looked at a plus h and we left b alone, or when we looked at f sub y, we did b plus h and we left a alone. Here we're going to change both coordinates simultaneously, but we're changing them simultaneously in a way that's moving us along this line here. So if h is 0.1, maybe we're right here. If h is 0.2, maybe we're right there. So we're going to move along this line as h is changing. And when we take the limit, of course, we're going to let h go to 0. We're going to imagine shrinking that. It's the same idea of a secant line rotating into the tangent position. That's going to be our idea. Okay, so here's the big picture. So we've got our secant line here, tangent line there, and now these two expressions are going to be so complicated to work with, we won't even use them once. Again, it's more of a conceptual thing. This is a change in y in the numerator, right? Change in y. change in function value, maybe I should say. Change in function value in the range divided by a change in domain position. Will?
Will MML try to make us use these?
Nope.
Oh, good.
No, it's too complicated. It's too messy. Yeah.
Let computers use it.
So you'll never use these particular definitions, but you should be able to understand what it means. The numerator is a change in function value. The denominator is a change in domain values. So h is the distance between a comma b, right there. There's a comma b right there. And then we have the plus a little bit in the a direction, plus a little bit in the b direction, which puts us over there. So this difference right here is h, that's down in the denominator, and then we go up to our function for both, and we take the difference, and that's the numerator, that's building this secant triangle. And so we have the rise over the run of the secant triangle, just like you did in Calc 1, the rise over the run for the secant triangle. And then we take the limit as h goes to 0, and that is going to give us the slope of the tangent line. That will be the slope of the tangent line. So any questions when you look at that picture? Do you have a sense of what it's trying to tell us? We build the line through there. We have 2 points on our line, which correspond to 2 points on the surface. We connect those 2 points with a secant line. And then we let h get closer and closer to 0. So we're shrinking in the domain back towards here so that this point is sliding along the surface until that point slides into the tangent position. And then the slope of that red line is going to be the rate of change in the direction of u.
So h kind of refers to what you do when you project that secant line onto the domain.
Yeah, h is telling us where our second point is. So we're taking the limit at a comma b, and when we add a little bit to a and a little bit to b, that's moving us along this line. And so as h goes to 0, that point's just moving along down here.
So h does not refer to the hypotenuse of the secant line.
No. 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 It's this direction.
Yeah.
It's the base of the secant triangle.
Yeah.
H is the base of that secant triangle.
Yeah, pretty much a line on the domain.
Yes. Yep. Question?
So this sort of reminds me of, I think it's the mean value theorem. Is that the right one where there's a point that there's a secant line that matches the
Mean
points?
value theorem is a little different, but the idea with the mean value theorem says this. It says if we create a secant line, and let's suppose that secant line has slope equal to something. 2. Then what the mean value theorem says is that somewhere, if this function is differentiable, so this curve is a differentiable curve, if you make this secant line, it says that there's somewhere in between A and B where there's going to be a parallel tangent line.
Is that like sort of relatable to the line and the secant?
Well, the difference is that with the mean value theorem, we're not pivoting off of one of the endpoints. When you're finding the limit, when you're rotating the secant into the tangent position, you're moving towards a fixed point. The mean value theorem is a little more general. It says, okay, well, somewhere between here, with the limit question that we're talking about now, we have our secant line here, and that secant line is rotating until it gets to the tangent position.
Okay.
So it's a little different, but it's but the mean value theorem does deal with tangent lines and secant lines and how they're related. So it's not totally different, but it's slightly different interpretation, because here we're fixing the left endpoint of our secant triangle. Okay, so that's what we got. And then down here they tell us the derivative of f in the direction of u is obtained by letting h go to 0. When the limit exists, it's called the directional derivative of f at a, b in the direction of u. So it's a mouthful.
In español, por favor.
So yeah, it's a lot. So we can call it, there's all sorts of shortcuts, but we're talking about, we usually just say the derivative in the u direction. We really mean the directional derivative, but you know what we mean. When we say the derivative in the u direction, or the rate of change in the u direction, we know what we mean. We mean the slope of the tangent in that direction.
Questions in this format, would we normally be limited in, I guess, the range of what we're looking at, or the domain we're looking at? Because
Yes. Yeah, we'll be zoomed into a position where, we're within the vicinity of AB, so we're kind of in this little region here. Now, once we get to the second partials test, we'll be looking at surfaces globally, and we'll say, hey, where are the high points and where are the low points? But at this point, we're just zoomed in on a point. We're saying, if we're standing on the surface, what's the rate of change in all possible directions? So we're sort of focusing on a single point at this moment. All right, so let's look at that definition right there. Okay, so that definition, again, really, really difficult. We need some sort of evaluation technique that's more practical. Trying to use the derivative formula back in Calc 1 was complicated enough when there was only one variable. Now we've got two variables, and now we're moving in a random direction, so it's much more complicated. All right, so here's what we're going to do. We need to build, if we can take that curve that's in the surface, if we can create a one variable function that tells us what the points are on that curve that's inside the surface, so it's a subset of the surface, then we're getting closer. So that's what this function g is. This function g, this is a curve in the surface. So this is a curve that lives in the surface, above that line that's down in the xy plane that's going through AB in the direction of u. So all we're doing, if we go back to here, and we look at the x and the y values right there, we're going to say, let's create this function where we're going to make it a function of s. And u1 and u2 are going to be the components of that unit vector. So the components of the unit vector are going to be scaled by s. So s is our independent variable. As s gets, it's like h. You know, we could easily call this g of h if we wanted to, but they wanted to represent the whole curve. H, usually we're thinking h is going to 0. You know, we have a different conception of what h is, but certainly you could treat h as the independent variable if you wanted. But they're just using s. So f of the, so this is a function of one variable. This is a function of s. Function of s, one variable. And this is just like what we just did. So f is a function of x and y, but x is a function of s, and y is a function of s, so f is really a function of one variable s, or g they call it here. So it's a function of just s. That means we can take its derivative. When we have a function of one variable, we can prime it. We can take the derivative of it. So notice that g prime of 0 is the derivative in the u direction. That's what it is. That's how we constructed it. If we take the derivative of this, this is that curve in the surface, so if we take the derivative of that, it's going to give us our rate of change in that direction of u. In the direction of u, because that's how we created it. We created it so that x and y are moving along the line in the u direction. So as s gets closer to 0, we get the derivative. All right, so now that's a function of x and y, which are both functions of s, so we can take the derivative using the chain rule from 12.5. So here's how we take the derivative. Let's rewrite the function over here just so we have it. We had that g of s was equal to a plus s times u1, comma b plus s times u2.
What are A and B?
Those are the points that are down in the domain.
They're just constant.
So yes, there's a constant point. That's AB right there. So that's a constant down in the domain. That's where we're trying to find the derivative at. So there's our a comma b right there. So we're getting closer and closer to a comma b along the line that contains vector u. Now, one thing that's a little bit funny is that normally wouldn't you put the coefficient of the variable in front of it? Like we would write 5x, we usually don't write x5. So it's a little funny that they did it this way, and I've seen it both ways in different books, but I would be more inclined to write it this way. This looks a little bit more normal when we think about writing lines in y equals mx plus b form, where the coefficient of the variable is in front, not after. But
In fact, maybe we could even flip around the point to follow mx plus b.
yeah, if we're going to write it in mx plus b form, yeah, and there are books that will write it like that too, so that it really models the exact form that we're most comfortable using from algebra. You could write it like that for sure. Yeah, write it in the USA form. USB. Okay, so let's do the chain rule like we just did in 12.5. So if we want to find g prime of 0, we'll evaluate at 0. They'll put this bar with the s equals 0 here to indicate that we're evaluating the derivative at 0. And somehow when I brought this over, dx ds, that's u1. This doesn't line up exactly how it did in the textbook. So that's u2 over there. So when we differentiate, first we're going to take the derivative with respect to x, or the partial with respect to x, and then multiply that times dx ds. And then we take the partial with respect to y, that's f sub y, and then multiply that by dy ds. So that's just the regular chain rule that we did in 12.5. And this is what it looks like. So partial of the function with respect to x, multiply by dx ds. Function with respect to y, multiply by dy ds. Dx ds is u1, dy ds is u2, and f sub x we can write in partial notation, subscript notation, f sub x. So we end up with that. And what we are going to do is peel this apart in a little bit. One observation, maybe I'll make it right now, is that you could imagine this as a dot product of two vectors, which we will do very soon. But you can imagine that f sub x dot u1, f sub x times u1 and f sub y times u2. So we can imagine it as that dot product of those things. We'll get to that though. So they refer to the directional derivative as a weighted average of the components of the unit vector. So this unit vector u, right? We're taking f sub x and f sub y, and then we're weighting them with respect to whatever the components of u are. So if u is 1, if the vector u is 1, 0, we get just f sub x, which makes sense. F sub x is the rate of change in the positive x direction. The rate of change in the positive x direction is f sub x. So when we choose our unit vector to be 1, 0, we get what we should, the partial derivative of f in the x direction. When the unit vector is 0, 1, we end up with f sub y, which is the direction, rate of change in the positive y direction. And if we're at some intermediate direction, we weight according to the u1 and the u2, which is interesting. So we can find all rates of change based on just f sub x and f sub y, and of course the direction that we're asking about. But if we want to know the rate of change in that direction, all we have to know are f sub x and f sub y, and then we create a unit vector pointing in that direction, dot them together, and we get that rate of change. So we will, and they call it a weighted average of the partial derivatives.
And with pretty much f sub x and f sub y, are they derivatives of the original f function that we saw?
Yep. Yeah, we said that g was, yes. So the original surface.
Okay.
So the original surface, we can find f sub x and f sub y, and then g is just the curve that's a subset of the surface.
I think I probably need an example to.
Yeah, we're getting there. So f is the whole surface, g is inside the surface, but aren't the g values just restricted function values for the surface? Right? If the curve is going through the surface, so we've got our surface, and then there's our curve, so the surface is z equals f of xy. The curve is right there, there's g, but the g values are the f values, but the f values have to be restricted to just analyzing function values along that line in the domain. Right?
You're blowing my mind.
Blow mind. All right, we better get to an example before
Yeah.
something crazy happens. We don't want anyone bleeding through the eyeballs. That would be messy. It's gonna get messy. Okay, so now they say let's use this dot product notation. So we're gonna have the partial derivatives dotted, the vector of partials dotted with the unit vector.
So does that get us a function?
This gets us a number, it gets us our slope.
It does get us a number.
Yeah, it gives us our slope.
Oh, because it's a dot product.
It's a dot product. Gives us a number.
Okay.
That's going to give us a number. All right, let's do it. All right, computing directional derivatives. All right, no more theory. Practice.
Let's do it.
So let's do it. We can do it. So f sub x is 2x. F sub y is negative 2y. So those are our partial derivatives. And now we're going to evaluate those partial derivatives at p. So I'm going to do f sub x of p, or you can write of -1 comma -3, or you could do f sub x of p. It doesn't matter. However you feel comfortable writing this, it doesn't really matter. And it looks like we only need the -1, so we get a -2. And then for f sub y, we're going to figure out f sub y at this point. Again, if you're more comfortable just writing f sub y of p, totally fine. When you start dealing with ordered triples, you don't want to write all 3 coordinates every single time. Just put a p. And that looks like it's going to be +6. They've given us our unit vector. Really, really important. That thing has to be a unit vector for this to work. Must be a unit vector. And now we can find the rate of change. So the derivative of f in the u direction at p, or at -1, -3. It's going to be the dot product, -2 comma 6, dotted with 3 over 5 comma -4 over 5. So whatever that works out to be, -6 over 5, minus 24 over 5, -30 over 5, which is -6. So that is our rate of change in the direction 3/5, -4/5.
So does that mean it's like a negative tangent line?
Yep. So if you walk in that direction, you're going down pretty fast.
Yes.
1 step, 6 floors. One step, 6 steps. One step. You know it.
One step this way.
Over 1,
6
down
steps.
6.
Yeah, there we go.
Yeah, that's steep. Steep. That's what you did in the lab today, right?
Yeah.
1 step.
Like this class.
1 step over, 6 steps down. All right, so all we need, it's so simple in a lot of ways. We just find the unit vector pointing in the direction of interest, find that unit vector, figure out our f sub x and our f sub y, dot the 2 together.
Will 12.6 homework be this easy?
No.
This is only the first example.
So
Yeah,
maybe
get
like
ready.
2 of the problems will be this.
All right, you guys try this one. I have faith. I have faith.
And what though?
In you!
Who is
In
the
the,
best
I know. In what? In the chaos of the universe. Faith in the fact that past, future, and present are all happening simultaneously. Have faith that we live in a hologram.
Me too, actually.
You're naming all these scientific theories, although none of them can actually, none of them fall under the realm of actual science.
Some of the integers is -112.
Okay.
I've seen that. It's fake. It's fake, yeah. It's fake unless you assume some really crazy stuff that.
I wouldn't say it's fake.
Yeah, maybe fake's not the right word. It's
Invalid?
non-traditional. Some of the positive integers is
So
-112.
is that like the right way to write what we're finding?
Yes.
Can you put like just
Mhm.
P? Okay.
Totally fine.
Okay.
Put of p, the rate of change in the u direction at p.
And then X.
18 times
50 plus 40.
90. She's right.
What did you say?
90.
90?
5 times 18, 50 plus 40. 5 times 10 is 50. 5 times 8 is 40. 40 plus 50 is 90.
144 over 32.
What's 144 plus 90?
134.
It's not 18, is it?
234 over 13. 18 times 5.
I got 18.
You get 18?
Yeah.
Nice. Hung.
So any issues finding f sub x and f sub y? We're going to have to come up with a name for f sub x and f sub y. What was that?
She goes, yeah.
Yeah, but we know we can ignore that.
Oh.
We can ignore that.
Oh, it is 18.
Ah. No trust either.
Yeah. You should know by now, right?
No wonder there's trouble over there.
What are you guys doing?
Just watching cartoons.
Oh my gosh.
What's
Fucking
that?
Rachel. This is why I'm
All right.
better on the test than you. What?
Okay, everyone agree that that's a unit vector? Yeah? So if we square, and add, just double check that it's a unit vector. 25 plus 144 is 169. The square root of that's 13. So that's a unit vector. So we multiply across, so we get 90 over 13 plus 144 over 13 equals 234 over 13. So that
It's 18.
is equal to 18. Right, thank you. So that is our rate of change in the direction of u.
So it's positive.
So we're going up.
18 floors for one.
Yeah, that's like flying.
Superman jumps.
It's like a helicopter, Superman.
Like a space elevator.
Space elevator. Up 18? That's quick.
That's
So
quick.
All right, space elevator.
Space elevators are slow.
Space
I
elevator.
did a whole physics project about this last semester.
Slow compared to what?
It's
You have
the
an knob
what?
and you're anchored to something.
The Wonkavator? Willy Wonka?
Yeah.
Yeah.
Yeah, you're right.
The Wonkavator.
You can't do it on the moon either. It's impossible to do it. It's entirely locked body.
All right, we need a name for this vector because it keeps showing up. F sub x comma f sub y. We need to call it something.
So let's call
It's
it
wanted.
gradient.
Let's call it the gradient. That's an excellent idea.
Obviously.
Why would we call it the gradient?
Great idea.
Why would we call it the gradient?
Because
Because it
sounds
tells you-
right.
Because it gives us the grade, right, of the tangent line. Gives us the slope of the tangent line. So, right, that's what it's going to give us. So the gradient is the vector of partial derivatives. The vector of partials. That's it. And when you look at this, this is the shortcut, funny math notation for it. We say that that's del f. That's how we pronounce this. Del. That is del f.
Like your Uncle Bill.
Uncle Del. Everyone's got one. And yes, all they did was take the triangle that you all know as delta.
And they fold.
They flipped it over and chopped off part of the name and called it del. Yeah.
All right.
Really creative. Really creative.
Their finest moment.
So del f is just part of delta.
If you take physics with Professor Melton, he'll tell you that the del operator is like a sledgehammer. You just take anything, you just start smashing it with the del operator, and you get answers.
Get answers. I never thought of the del operator as being so violent. The del operator massages functions and gives you rates of change. It's not so-
Massage.
Nice.
right?
Maybe an elephant massage.
Watch out for that del operator. Okay, so does everyone understand what the word operator?
It operates on.
They like transfer you from one person to another on a phone call.
They don't still have those, do they?
Sometimes.
Do they?
I don't think so.
Call your doctor.
So a function, when you hear the word function, you think of a function as taking one number and turning it into another number. So a function acts on real numbers usually. Could be complex numbers, but usually you say f of 5 is 3. An operator does the same thing for functions. An operator takes a function and spits out another function. So an operator is a function on functions. So when we do del f, it's giving us another function. So we're taking the function f and we're getting out something else. Now in this case, it's a vector valued function because we take our function f and we apply this operator and we get out a vector function. So an operator acts on functions, like a function acts on numbers. So it's kind of one step up. Okay, so if we take this notation, we can rewrite the directional derivative of f in the u direction like that. And we already know some theorems with the dot product. We know that the dot product can be written as the following. So we had this back in the old days. We wrote this as, if we had u dot v, we wrote that as the length of u times the length of v times the cosine between them. So we're just doing that. We've selected u to be a unit vector. So that part just goes away. And so now we end up with just the length of del f multiplied by cosine of theta. And a couple of points to focus on here. The length of del f, that's going to, if we plug in ab, this is going to be a number. And it's going to be a positive number, or at least a non-negative number because of the absolute value bars. Cosine of theta, though, that could be positive, or it could be negative. But the most cosine can ever be is positive 1. The least cosine can ever be is negative 1. So the largest value of the derivative of f in the u direction, the largest this could ever be is when theta is 0, so that cosine of theta is 1. That's the biggest this could ever be. Does everyone agree with that? Because if you choose another theta, your cosine value will be a fraction. And when you take a fraction of a number, you're shrinking its value. So the most this can ever be is when theta is 0, and it will be equal to that. The least this could ever be is when
Theta's pi.
is that pi. Then cosine of pi is negative 1, so then we get negative 1 multiplied by whatever this quantity is. So the directional derivative is going to move from negative absolute value of this to positive absolute value of that. So that's the range of possibilities for the directional derivative. Okay, so here it says that it has the max, cosine is, cosine of theta is 1, blah, 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 blah. All right, that's what we just talked about. Okay, now, the gradient is a vector in two-dimensional space. It's f sub x comma f sub y. It's in two-dimensional space. So you should think of the gradient as down in the xy plane, in the same place that that unit vector u is living. So if we stand on the ordered pair a comma b in the domain, the surface is above us, our vector u is pointing in the direction of interest, the gradient is also a vector down there pointing in some direction. And what we need to figure out is the geometric interpretation of the direction that the gradient is pointing. That's going to be a very important direction. So we're standing on the ordered pair a comma b. We have our unit vector u, and the gradient is going to be pointing in some direction. And there is geometry to the direction that it chooses to point in, which we will figure out very quickly. Okay, so gradient lives in the domain. It's not on the surface. So surface is up here. Down there is the domain with u and del f. They're down in the domain, not on the surface. Okay. Now, f is the surface, and f has its maximum rate of increase in the direction of the gradient. So we will prove that that is true. The gradient is going to point in the direction of steepest descent, the direction of maximum function increase. So it's down in the domain, and the direction the surface is climbing most quickly. If you look down in the domain, that little gradient vector is pointing in that direction. So the gradient points in the direction of maximum increase. And that rate of change is going to be the absolute value of del f as a point AB.
So when cosine is 0?
When theta is 0 and cosine of theta is 1. So if we choose our unit vector, so we're standing on AB, the gradient is what it is. The gradient is pointing in the direction of maximum increase. If we take our unit vector u and position it so that it's pointing in the same direction as the gradient, so theta is 0, that will be the direction of maximum increase. So the gradient will always be pointing in that direction. And if you turn 180 degrees, -1 times the gradient is pointing in the direction of maximum decrease. So if that direction is maximum climb, that direction is maximum descent, quickest descent, 180 degrees away. So f has its maximum rate of decrease in the direction opposite the gradient, and that rate of change is -1 times the absolute value of the gradient. The directional derivative is 0, orthogonal to the gradient. Rate of change is 0. What comes to mind when you think of a rate of change of 0 with respect to a surface?
Maximum or minimum?
What's that?
Maximum or minimum?
Max and mins, that's one thing. But
Traces?
so the thing that's different, so maxes and mins, we're going to have more than just a one derivative being 0. Because if you think conceptually about a max, you're going to have a horizontal tangent plane on there. And if we have some curved surface, you can imagine a tangent plane that does have a line in it that has slope of 0, but it doesn't necessarily mean all of the lines have slope of 0. But there's one other feature of a surface we've talked about that has to do with constant function values.
Traces?
It's like a trace, we call them level curves. So a trace is a specific intersection of a surface with a coordinate plane.
Right.
But the level curves are the curves of constant height, the curves of constant function value.
Where it's like flat.
So if you are imagining your surface, and if you were to walk along a level curve, what would your rate of change be? 0. And by rate of change, we mean the altitude, right? The function is measuring how high you are above the xy plane. So if you walk along a level curve, df should be 0, right? Your directional derivative, if you go tangential to the level curve, your rate of change is going to be 0. We're going to follow that? So if you're walking along a level curve, you're not going up or down, so the rate of change is 0. Because the rate of change is measuring up and down movement when we're talking about a surface. So that's what this is implying. So the directional derivative is 0 if you're orthogonal to the gradient. So in other words, the gradient is perpendicular or orthogonal to level curves. Level curves also live in the domain. So we've got our surface down in the domain. We are standing on point AB. We've got the gradient. We've got our unit vector. We've got our level curves. Everything is down in the domain. And the function values are up on the surface. But all that stuff is down in the domain.
Are level curves projections of the surface? Is that what you're saying?
Level curves are projections of the contour lines down into the domain. Yeah.
So you're telling us level curves are P and the gradients are P perp, and U is the distance to that point.
That's, I think, that's at least almost correct. So, say that again. So U in the gradient.
No, yeah, so P perp is the gradients,
P perp is the gradient.
P is a level curve,
P is level curve.
and then U is some point up the top. Or that,
Yeah.
I don't know about you. That U's the only one I got.
Maybe we'll take you out of that picture.
Yeah, we'll take you out of that.
Take
picture.
you out of that picture. So then U, so the vector U and the vector, the gradient, they're acting kind of like P and P perp were acting, or how U and V were originally acting, and we created P and P perp. So yeah, so what you are saying though is that we can imagine writing vectors in the domain as combinations of the gradient and the tangential, the v, the derivative, the v vector. Okay, let's do this right. Let's take a 10-minute break, and then we'll start doing some applications here where we'll stop talking theory, start doing some problems. All right, so let's see if we can make it work. Direction of steepest ascent and descent, consider the following functions and points. So first it says find unit vectors that give the direction of maximum ascent and descent. Steepest, maximum rate of change, minimum rate of change. Books use a million different expressions for that. Maximum rate of change, minimum rate of change, direction of steepest ascent, direction of steepest descent, all sorts of different ways to talk about it. So first let's find the gradient. The gradient is a vector. It is the vector of partial derivatives. So we can write it quite simply like this. The gradient is a vector in the domain. Bless you.
Thank you.
We can find the gradient at a point. So the gradient at point P, we plug in the x's to be 1, the y's to be -2. So that is the gradient vector at P.
Then we take the magnitude.
Find the magnitude. That will give us the maximum rate of change. What's that? 4 plus 256, which is the square root of 260. That's divisible by 4 because 60 is. So what is that? 4, so it's going to be 2. Square root of 65. All right?
Yep.
Okay, so that's our maximum rate of change. So it says now, let's try to answer the question. So in part A, it says find unit vectors that give the direction of steepest descent and steepest descent. Okay, so now we've got our data. What's the unit vector going to be?
X over root 65, -4, y over root 65.
So the Umax, we're going to take the gradient and divide by the length of it. So we're going to take the gradient, divide by the length of it. So we're going to divide by 2 root 65, so we get 1 over root 65, comma 8 over root 65. So this will be the direction of maxima of steepest descent or maximum rate of change. And it's a unit vector. The unit vector that points in the direction of minimum rate of change or maximum descent, we multiply by -1. That's it. Okay, so that's part A. And it didn't even ask us though, so the rate of change, so the max rate of change is going to be 2 root 65. And the min rate of change
This is negative.
is -2 root 65. All right, part B. Part B says, find a vector that points in a direction of no change. It says find a vector.
Orthogonal.
So we want to find something orthogonal. So for part B, we want something orthogonal to that. So we switch the components and switch the components and do what?
Make them negative.
Yeah, change one sign. Doesn't matter which one. We could do that, or we could switch the other one. There's going to be 2 unit vectors that we could choose from. It just says find a vector. So one of these 2 would work. So that's no change. So those are going to be along the level curves. Those will be tangent vectors to the level curves. All right, go ahead and try this one. Same thing, 29. Back up. So 260 is 4 times 65. 260?
Yes.
We can write that as 4 times 65. So
Yeah, so, okay, so I know for this one, you find the x and then plug in the magnitude of it.
yes.
And that's where you get the
Yes, so the maximum rate of change will be that.
Square root of 5, anyone? Square root of 5?
Yes.
Okay.
and then
Yep, yep. So the U max, so we do 2 divided by 2 root 65, and we do 16 divided by 2 root 65. So the gradient vector 2 comma 16, we divide both of those terms by 2 root 65, and then the 2 cancels.
and to unitize it, you just take.
That does unitize it. So 2 comma 16 is not a unit vector, but if we divide it by the length of the vector 216 is 2 root 65, so if we divide that into both those terms.
Oh, you're dividing it by 2, and then the canceling the 2.
Yes.
Yes, I'm sorry, that's where I got.
Make sense?
Yes, yes.
And then the min rate of change is always just minus 1, so it's like x rate of change.
Yes, I got lost because I'm like, look at the 2 that now I have to think.
It was just that happy coincidence, right?
Happy coincidence. Happy coincidences.
A
Coincidence.
different B, but, yes.
All right, we ready to roll? Well, let's see. So the gradient. Oh, it's so nice having a name for this vector now, isn't it? So 4x cubed minus 2xy, comma. So we partial with respect to x, and then we partial with respect to y. So that'll be our gradient vector. Again, the gradient lives in the domain. Yeah, question.
Do you need the vector symbol above the del? Isn't it implied
It's not. It's not.
Usually we'll put, anytime on the board I'll put it, but because in the book they just make it bold.
Okay. Is it okay if we don't use it for that instance?
I'm fine with it. Usually if you put the vector symbol over it, it helps reinforce that it's going to be a vector. I'm trying to think of a situation where it wouldn't be a vector, but del is
you're
always
right.
a vector,
Okay.
so.
Yeah.
So, yeah, so you can get away from that in a minute.
That's what we were
Yeah, it's
just-
not, it's, question?
We all got the same one.
2y.
It's 2y, not y squared. At the very end.
Oh, partial with respect to y, thank you.
Mr. Boss is a cube.
Yes, yes. I was just making sure that you were following how
Paying
to do
attention.
partial derivatives. Okay, you're on track. Excellent. And then we evaluate it at our points of interest. So del f at -1, 1, or at p, however you want to put it. And just plug in -1 for x, 1 for y. So what do we get there? Looks like -6. Do we agree? No. We don't
2
agree.
and 1.
No. Do we get a 2?
I got 2 and 1.
I got -2, 1.
-2, 1.
Negative.
Well, let's see. So that's -1 plus 2. That's +1. That's going to be -1 times 4 is -4 plus 2. Yeah, I agree. -2, 1. Okay, so length of the gradient vector.
Root 5.
So length of the gradient vector at this particular point is going to be square root of 5. All right, so that tells us that the maximum rate of change is root 5, and it's in the direction of the gradient. So the unit vector that points in the direction of maximum increase is going to be -2 over root 5, comma 1 over root 5. Pointing in the direction of maximum increase.
Wait, hold on.
Yeah,
Can you scroll up all the way to the top?
all the way to the top.
Why did we drop the negative for this? Oh. Carry on.
Carry on. Carry on. No dropping of negatives.
I was gonna say that was a lot.
No.
No dropping of negatives. All right, so then the unit vector that points in the direction of steepest descent, maximum decrease is that. We multiply by -1. And then our max ROC, our max rate of change, is root 5. And our min rate of change is negative root 5. So, not as steep as the other one we were looking at.
What about the part B?
What was part B? Tangent vector. So tangent vector, so no rate of change. So no rate of change. We switch the components and change a sign. So we could go 2 over root 5, 1 over root 5. Or minus 2 over root 5, minus 1 over root 5.
Didn't
But you didn't switch components
switch
the
the
first time.
components. Or
I didn't switch them? What am I doing?
I don't know.
I don't know.
Weird math.
We did not switch them.
I'm like so wrong.
Switch. Switch the components. That
So
word's
you get 2 positives for one and 2 negatives
2 negatives for the other.
Okay.
There we go.
Okay.
So if you have one negative, then how you introduce another negative.
Mm-hmm.
Okay.
Or take one away.
Okay.
And so remember that the dot product for two vectors to be perpendicular, dot product has to be 0, so we just double check. So that's going to give us a negative, that's going to give us a positive, same magnitude, so we get 0, and same for that one. So those will be the 2 unit vectors that are tangent to the level curves. Okay, gradient and level curves. Okay, so we are going to prove that the gradient is, we're going to look at some examples and see that the gradient is in fact orthogonal to the level curves. And if it's true, which it is, we can come up with another way to find the equation of a line. Exciting. So you know how we found the equation of a plane by doing n dot v equals 0? If you know that you're in a plane, couldn't you, if you wanted to find the equation of, say, this line, and we knew that this was perpendicular to that line, couldn't we form the equation of this line by doing n dot v equals 0? If we know we're in 2-dimensional space, and we know that n is orthogonal to this line, we could build the equation of that line by using a similar process to how we built plane equations. It's possible.
How would we tell the difference between the line and the plane, though?
You tell me. What does the equation of a plane look like?
Different than the equation.
Ax plus by plus cz equals
D.
d.
Yep. So equation of a plane has x, y, and z in it. The equation of a line will be down here. It's in 2-dimensional space, so it's going to be ax plus by equals c. So we know because of the number of variables.
Yeah,
All right.
so we're only working
You
two
can tell
space.
because of the way it is.
It is
It's
what
different.
it is. Same but different. So we are going to come up with this. So here's how we're going to imagine. So we're going to think of del f. Del f is going to be normal to the line that we're looking at. And then this is the displacement vector that's on the line. X minus a, comma, y minus b. So if we look at this picture right here, we're imagining x comma y as a point right there. And here's our a comma b. And we just form that displacement vector. And that has to be orthogonal to n, so the dot product has to be 0. So we end up with this equation. So the gradient is f sub x comma f sub y. And then a displacement vector in the direction of the line is x minus a comma y minus b. X minus a, y minus b. And you can conceptually think about it like this. The tangent line is the collection of all points that form displacement vectors with AB that are orthogonal to the gradient of f. We can think of it that way. So the idea, we've got our curve down in the xy plane. We form the gradient vector, which we now know is, so this is a level curve down in the xy plane. That's in the xy plane. We know that the gradient is going to be orthogonal to that. So maybe the gradient is right there. At this point, we'll just suppose that this is our point of interest. So that's going to be del f of a comma b. That's the point a comma b. And if we want to find the equation of this line right here, this tangent line, let's make it at least appear to be perpendicular. So if we want the equation of that line, we are going to imagine a displacement vector in the line. So that's going to correspond to the ordered pair x comma y. So that line is going to be the collection of all ordered pairs x comma y such that this is true. So del f dot v equals 0, which tells us that we have f sub x comma f sub y dotted with x minus a, y minus b equals 0. So that's how they come up with that equation just above. F sub x times x minus a plus f sub y times y minus b equals 0. So that's just another way to find a line in two-dimensional space. Feels like something's missing though. And I know what it is.
Great.
Because you don't always know the surface, right? So if we're trying to find, so what I've just said is that if you have a level curve, you can find the equation of the line, right? But how do you get a level curve? Well, you have to have a surface, right? You have to have a surface first. So it feels like something's missing. If we just say find the tangent line to this curve, then you say, well, what about the surface? How do I get del f? How do I get del f? If you just give me a curve. Right? Feels like something's missing. Because if you're given a level curve but you don't know what the surface equation is, it feels like there's something missing. We'll discover in a moment that there's a way to remedy that. Certainly if you start with the surface, it's not a problem. Okay, so here we're just talking about more directional derivative stuff. So it says find the gradient of this function. Let's do that. That's not too hard. We now know how to find gradients. So del f will be super easy when there's no mixed terms. So that's our gradient function, vector valued function. And we can find the gradient evaluated at p. And that makes it easy when the x's are in one component and the y's are in the other. We don't have to do too much thinking. So we get that. Okay, so that's part A. We found the gradient. We evaluated it at p. Find angles theta with respect to the positive x-axis associated with the directions of maximum increase, decrease, and zero change. Okay, so we're over here. Let's draw a little sketch. -3, -1. We're in quadrant number 3. Just sitting over here at -3, -1. That tells us that at that point, the gradient is -6, -6, so the gradient is pointing this direction. That's del f. Okay, so what's an angle for the direction of maximum increase?
5 pi over 4.
5 pi over 4. So if we imagine a little coordinate system right there, the angle is always measured from the positive x-axis, so it's going to go that way. So that would be 5 pi over 4. So that'll be the angle for max increase, 5 pi over 4. And theta for the minimum increase or maximum decrease, however you want to think of it, will be pi over 4.
Are they always multiples of pi over 4?
No.
Okay.
Why would they be?
I don't know.
If the I mean, it just depends on how x and y are related. Because, right?
Okay, I
Yeah.
see that now.
Yeah, it's not always multiple of pi over 4. Unless x and y have
I'm
the
just
same.
trying to find a pattern
I know.
here.
Unless x and y are,
Make
you know,
it simpler.
related properly.
So theta is calculated off of the point del f of p.
Yes, exactly. So our point of interest is right down here, -3, -1. So the gradient is always applied right at that domain point. And now we can't picture the surface. The surface is that, well, maybe we can picture it. This is a elliptic paraboloid sitting above this. And so this is a domain point that corresponds to a point on the surface. And if you were to walk on the surface in this direction, it would be the direction of maximum increase. Yes, exactly.
Do like tangent of y over x, because it's definitely going to be tangent of 1, but we know we're in the third quadrant.
Yes, that's right. So we know we're in the third quadrant because of those signs. So yes, if these were numbers that weren't easily managed, we might have to use a reference angle. So if this was something like -1, -5, and we wanted to find that angle, we would do inverse tangent of 5, and then we would add it to 180 degrees or to pi radians. Yeah. So if it wasn't easily discernible, does everybody understand what we just said? If the vector happens to be a vector with components that doesn't give us a special angle? Does everyone remember how to do that?
Because that'd be like tangent of 5. which
So
is not.
yeah, let's just suppose,
Or inverse
let's
tangent
come
of
off to
5.
the side for a second, and let's just suppose del f was -5, -1. So that's not giving us an angle that we're familiar with. So we would, if we wanted to find theta, we would say tangent of theta prime. Tangent of theta prime, that's the reference angle, that's going to be 1/5. And so theta prime is going to be the inverse tangent of 1/5. And this one's a little misleading because I'm taking the absolute value of y over x. When you find a reference angle is always a positive acute angle. So we're taking absolute value there. This turns positive anyway because of the negatives. So what do we get rounded to the nearest degree for that? Inverse tan of 1/5. Let's do it in degrees. Radians, when we're not dealing with special angles, that's a painful. 11 degrees?
Yeah.
So we get about 11 degrees. So now if we wanted the answer, we wanted theta, what would our theta max here be then?
191.
Yeah, 191. Because in quadrant 3, this is a quadrant 3 angle. Reference angles for quadrant 3, the reference angle is always right there. And so we would have to add the reference angle to 180 to get theta. So theta will be 180 plus whatever theta prime is. So we do 180 plus theta prime, so we would get 191.
But if we weren't in quadrant 3, let's say we were in quadrant 1, we wouldn't add anything to it.
Yeah, theta 1, the reference angle is itself. Yep. And what about in quadrant 2?
Add 90.
Subtract from 180. The reference angle is always between the positive x-axis and, so if we're here, there's theta prime, so theta is equal to 180 minus theta prime. So if this was negative, let's suppose that we had del f being -5 positive 1, then tangent of theta prime is positive 1/5. We take absolute values. We get theta prime equals 11 degrees, and then theta is going to be 180 minus 11 degrees, giving us 169 degrees.
Because you know it's in quadrant 2.
Because we
so the
know it's in
signs-
quadrant 2.
Okay.
So the reference angle we find by taking absolute values, and then we have to apply it, based on the quadrant.
And then for the last part of the question, where it's the beta with 0 change, so that's the orthogonal, so like in this case you just have 90 instead of the 180?
Yes, exactly. So for this one, for part C, part C says write the directional, oh wait, we're not there quite yet. But yes, what you said is true for the direction of no change. Direction of no change. So the direction of no change is going to be at 3 pi over 4 and 7 pi over 4. Okay, so let's see. So, it was still part B. Sorry, I missed that part. So the end of part B says also 0 change. So the angles for 0 change, we'll call it 0 theta sub no change, theta none would be pi over 4 or 7 pi over 4. Everybody okay with that?
No.
Can you explain that again?
Oh yeah, I'm not okay with that either. 3 pi over 4. 3
I was
pi.
gonna say we have pi over 4 and the pi.
I got caught up by the pi. 3 pi over 4, 7 pi over 4. We agree with that? Yeah. So the directions of no change will be orthogonal, will be perpendicular there. 3 pi. Yeah. 3 pi over 4 and 7 pi over 4. Okay, part C. Find the directional derivative as a function of theta and call it g. All right. This one's hard to conceptualize. So let's read it a third time. So write the directional derivative as a function of theta. Directional derivative. So the directional derivative.
What was C?
Pardon?
What was C?
That is C.
Okay, sorry.
It is C. That's what we're trying to figure it out right now.
Gain our C's. I'm getting my C's and D's mixed up.
C's and D's. All right. So a function of theta, call it g. So we're trying to find a function of theta. This is going to be the directional derivative. G of theta. Directional derivative of f in the u direction. So we know that it's the gradient multiplied by a unit vector. Gradient multiplied by a unit vector. So it's going to be gradient, which is f sub x comma f sub y, multiplied by a unit vector. Let's see, let me move that a little bit. All right, can somebody tell me a unit vector that points in the direction of theta?
Negative 1 comma negative.
But we need it to be a function of theta, so it's got to change. Right, so
Cosine theta.
cosine theta sine theta. Isn't cosine theta sine theta the unit vector that points in the direction of theta?
Because it's 1 when you square them both.
Right, so that means it's a unit vector. So this, and we did this back in the first chapter we worked on when we were scaling unit vectors for those force problems. If the force goes in direction of theta and its magnitude is 50, we said that the vector would be 50 times cosine theta sine theta. So cosine theta sine theta is the unit vector that points in the direction of theta.
But will we still, we'll still have x's and y's in there?
Hopefully not, because
because it's -6, -6.
yeah, f sub x, f sub y is at a particular point is a vector of constants.
So we do use the point.
We will use the gradient evaluated at a comma b. So the gradient at a comma b is -6, -6. So -6 times cosine sine.
You're dotting those, right?
Yep, dotting those together. See if we can squeeze it in here. So -6 cosine theta minus 6 sine theta. So this is our function g. So that function g is measuring the rate of change in the direction of theta. So we've now written the directional derivative as a function of theta. And so we should be able to make the same conclusions that we just made by using our theorem. Our theorem said that the gradient points in the direction of maximum increase. So when we want to figure, if this is measuring the rate of change in the direction of theta, how do we figure out the direction of maximum rate of change?
Where's theta max?
How do we find theta? If someone gives you a function and says, find the direction or find the value of theta for maximum rate of change, what do you do?
Take a derivative.
Take the derivative and set it to 0. Right? If someone says, here's a function, find the place at which it has maximum rate of change. Do you agree? So we want to find, if we want to maximize this function, we take its derivative and set it to 0. And we should get the same answer. We better get the same theta, right? G prime of theta is going to be minus 6 sine theta. If I differentiated, no, that's a negative, derivative of cosine is negative sine. So then,
What's this cosine?
Minus 6 cosine.
so we get that. So that's a plus right there. Let me just get rid of that little, we don't need that. Okay, so that's the derivative. We set it to 0. We want to maximize it, so we set it to 0. And that tells us that, right, tangent theta is equal to 1. If we set it to 0, we get 6 sine equals 6 cosine. Divide by 6, so we get sine equals cosine. Divide both sides by cosine, and we get tangent equals to 1, which gives us the same guys here. So the max is going to be in quadrant 3 where the tangent is 1. That's at 5 pi over 4. The min will be pi radians away from that, which will be pi over 4. So this gives us the same exact theta max. This tells us theta max equals 5 pi over 4. Gives us the same exact max.
But we still need added information to determine that it's 5 pi over 4, as opposed to anything else, or it's like a.
No, we don't need any extra information because we know we're in quadrant 3.
Well, but don't you need like extra information so you know it's not like a horizontal tangent or something of that sort that also has a rate of change of 0?
But we're talking about so.
Like just in general, not necessarily for this one, but like.
It's
Because,
just like the unit circle.
Yeah, but like we're trying to find points of interest, right? And so points of interest could be max, mins, and horizontal tangents.
Yes, but now we're dealing with a surface, though. So we're dealing with a surface and a point for the surface. So we're not. So if we're talking about the characteristics of the surface, like maxes and mins, we're definitely not there yet because we need more information. We need tangent plane information. So at this point, we're just thinking about the surface. We have a point of interest down in the domain, direction of maximum increase, direction of maximum decrease. That's all we have right now.
Okay.
So we're given, we know that we're going in quadrant 3 because of the gradient.
Okay.
So we know we're in quadrant 3 because of that. And then we're just trying to figure out then, so this is just an alternative way to figure out the 5 pi over 4 and the pi over 4. Are we going to use that as a general method? No. They're just trying to get us to think conceptually that we could write the directional derivative as a function of theta, and based on stuff we know from Calc 1, we could maximize and minimize that function by taking the derivative and setting it to 0. So we are definitely, so this is a totally different curve, right? This is a curve in and of its own right. That's, you know, some wiggly thing. But we do get the same exact max value. Yeah?
Is it possible that using this method and we get the theta, we get our tangent theta equals 1, is it possible that the theta is our min, like 5 pi over 4 is the min, or is it always going to be the max?
It depends on what these guys are.
Okay.
So right there, so if we know we're in quadrant 3,
right,
when tangent is 1, in quadrant 3 where tangent is 1 is 5 pi over 4.
Right.
If we're in quadrant 1 where tangent is 1, then we're at pi over 4.
So if it was 6, 6, the max would be pi over 4.
Yes.
Okay.
Yes.
That makes sense. Okay.
So if we were going in the direction 6, 6, so if it was like that, then we are pointing into quadrant 1, then we would, then we would use pi over 4 as our max.
So if you just knew G sub theta, you couldn't tell which direction the max or.
Right. We have to have del F to know which quadrant we're in. Definitely need to know the quadrant. Was there a D on this too?
Yeah.
Oh, and an E?
Well, we
We just did D. Okay, phew. Verify that the value of theta maximizes G corresponds to the, we already did that too.
We just talked.
We talked about it. There's no more space. There's got to be a way I can split a page, but I don't know how to do that. There must be a way.
He's got some problems.
There must be a way. But let's not figure that out now. Okay. Level curves. Let me see how many slides we have left. I want to make sure we can finish this. Okay, consider this paraboloid. Everyone visualize that paraboloid. What direction is it open? There's only two choices.
No.
Is it opening up or down?
Down.
Down. Right? Z equals negative x squared, negative y squared. Opening down.
Like, I don't
They're negative.
Right?
16 minus x squared over 4 minus y squared over 16.
That is a paraboloid that's opening down.
Is
You
it
guys
like,
are killing me.
is it stacked?
What are the slides?
Is it what?
Is it stacked like 16 minus x
It's
squared
just
over 4
formatted
minus
so
y
badly
squared?
that it's hard to read it.
16? Is it like,
Yeah. Those are stacked. Yes.
Is it?
it just looks odd.
It looks really weird.
So,
Like that could easily be
Oh.
16 minus
Oh,
x
okay.
squared over
Oh,
the
okay.
quantity of 4 minus y squared.
what I was
Technically not. There's something
That
called the
would be
order of
parentheses.
operations.
I thought they were like, instead of commas, they were just like slashes.
Yeah, that's what I
to
thought too.
highlight.
Oh.
Okay, you
I
guys
was
are
like,
seeing
what?
what I'm seeing, right?
We need to have a reading math part of our course. Math reading. Yeah, no, they should. Yeah, I don't know why they
I
didn't
think
stack
math.
it though.
I think computers need more math reading 101 than
Yeah.
we do, so they understand what you're saying and take.
Have you looked at a math book from the 70s?
Yes.
Oh man. Oh boy. They couldn't even do the exponential function. They would write an exp of x
What?
for e to the x.
That's
Yeah, total hassle. Okay, and that's why the arc functions, they used to always write, instead of sign with a little -1, it was always arc sign.
Okay.
Before they had all the ability to typeset.
So the reason you guys do arc sign is old habits die hard.
Yeah.
You want to impose the pain on us too.
I suffer, you should suffer. Okay, so we have a paraboloid. Everyone see the paraboloid opening down? Right? The top of it's up at 16, and then it's going to open down, and each cross section is an ellipse. If you let z be 0, you're going to have the ellipse with 16 on the right. You would divide by 16 to get the standard form. Okay, so that's a paraboloid opening down. Not that we need to know that for this problem, but. Okay, so P is on a level curve. It's on this level curve. So we're going to assume that that's correct, that if we plug in 12 right there, that this ordered pair satisfies the equation for that level curve. We'll assume that they did that right. Compute the slope of the line tangent to the level curve at P and verify that the tangent line is orthogonal to the gradient. Okay, so we've got our surface. We're going to take a cross section, which gives us an ellipse. We're projecting that down into the xy plane, which is called the level curve. So we've got this curve. When we set that equal to 12, that's a curve in the xy plane. We have a point on that curve in the xy plane, tangent line at that point to the level curve. So let's do it. All right, so 12 equals 16 minus x squared over 4 minus y squared over 16. Let's rewrite this so that we have x squared over 4 plus y squared over 16 equals 4. All right, so there's our level curve in the xy plane. It's living in the domain. And that point's on it. That point's on it.
Yeah.
Okay, so compute the slope of the line tangent to the level curve. So last class we learned a very clever way to find the slope of the tangent to an implicit function. So if we want to figure out what dy dx is, that's the slope of the tangent line. If we want to figure out what that is, we could implicitly differentiate this with respect to x. Or we could use that clever method that was quicker. We can say, hey, let's define a function that has, well, we are actually, oh, why did so much disappear? Okay, so what we did last time was that we defined a capital F, and then we used minus f sub x over f sub y. Remember that?
Partial.
No.
You remember.
Come on,
Yeah.
you remember.
Yeah.
So we did dy dx is equal to negative f sub x over f sub y.
Oh,
You did that?
yes.
Right?
We can do that.
That thing. We
yes.
can do that. So we can do it. We can do it. So I'm
Let's
going
do
to
it.
define capital F. Capital F, let's define just to be the left side of this thing. We've got that.
Because your constant goes away. Right?
Constant we don't care about. We're about to partially differentiate, and partial of a constant is 0. So then dy dx is minus f sub x over f sub y. And so that's going to be, when we look at f sub x is going to be 2x divided by 4, so that's x over 2. There's still a minus sign. F sub y is going to be y over 8. And so this is going to equal, if we keep on trucking, what do we get? The 8 goes up top.
4y over x.
4, so is it minus 4x over y?
Mm-hmm.
Minus 4x over y. And then we evaluate it at our point of interest. So dy dx at p will equal negative 8 root 3 over 4. If I divide it right.
So we just get negative 2 root 3?
Negative 2 root 3. Okay. So that is the slope of the tangent line to the level curve. Slope of the tangent line to the level curve. It's the slope of this ellipse at that point. Slope of a curve is the same as the slope of the tangent line. That's what we mean by the slope of a curve. The slope of a curve is defined to be the slope of the corresponding tangent line. So you can say that's the slope of this curve at that point, or you can say it's the slope of the tangent line to this curve at that point. Yeah?
It's a tangent line, though. It's not a tangent plane.
Tangent line. We're in the xy plane. That's an ellipse in the xy plane, so yeah. We're down in the domain dealing with curves, not up in the surface dealing with 3 dimensions.
So that's why you said it's the tangent line of a level curve.
It's the tangent line of the level curve. Yep.
Okay.
It's the slope of a curve, slope of the tangent line. Right there. Okay, so that was the first thing they asked for. Compute the slope of the line tangent to the level curve at P. And now it says verify that the tangent line is orthogonal to the gradient at that point. So let's come up here and let's figure out what the gradient, ooh, interesting color. The gradient of f, and actually I guess I should do it from here. The gradient of f is minus x over 2 minus y over 8. Everyone okay with that? So z, this is f, this is the function, the derivative of this with respect to x, negative 2x over 4, so we get that. All right. And the gradient, that's a terrible color. And the gradient at our point P, we plug in our point P, what do we get? Plug in 2 root x, what's that, minus root 3?
Minus 1, 2.
And what's that one? Minus 1/2? Is that right? 4 divided by 8 with a negative, okay. So, the gradient, let's figure out what the slope then, that's a vector. What's the slope of the gradient vector? The slope of the gradient vector at P is y over x. Y divided by x, so 1 over 2 root 3. That's the slope of the gradient. Now how do we know that the slope of the gradient and the slope of the curve, how do we know that those two things form a right angle?
Donna.
Close. We don't have vectors.
True.
Reciprocals.
Yeah, opposite reciprocals. The product of slopes for perpendicular lines has to be -1. If you have two lines that are perpendicular, the product of their slopes is -1.
That's freaking awesome.
And if you multiply those two together, you get
-1.
you get -1. Yay! Does everyone follow that?
Yep.
So the gradient, we found the gradient. We have our surface. We found the gradient. The gradient is a vector. If we want to find the slope of the line that passes through that vector, we just do y over x. So that's the slope of the gradient vector. We also projected down onto the xy plane. We have a curve in the xy plane. We calculated the slope of the tangent line to that curve using all this stuff. So there's the slope of the tangent line. There's the slope of the gradient. They multiply to -1. That means the gradient and the tangent line are perpendicular. Question?
Does that have anything to do with like curvature and radius of curvature?
Not really.
Because I guess those aren't negatives. Those are just
Yeah,
positives.
yeah. We're just so this is really just back to algebra, where you know that two lines are perpendicular if their slopes multiply to -1.
Check it out. Algebra.
Right? That's
Algebra.
back to algebra. This is a moment of relief. Back to algebra.
Moment of
A
relief.
moment of relief. It's like, oh, it's just algebra.
After you do all that calc 3 stuff.
After all that calc 3 stuff, it's like, oh, it's just algebra. It's just algebra.
But
all
that's
right?
where we messed up.
I know. That's the part that's easy to mess up. So let's do another one like this. So consider the upper ellipsoid, the upper half of the ellipsoid, the semi-ellipsoid? No, hemi-ellipsoid? What do we call it? Hemisphere, hemi-ellipsoid?
Hemi-ellipsoid.
The upper half of the ellipsoid.
It's got to be a hemi.
Semi-hemi.
Hemis? No, hemi?
We'll just call it a hemi.
Call it a hemi?
Oh, that was funny.
Call it a hemi.
Half of
You
it.
man,
All
can
right.
you spot me a hemi?
Yeah, let me pull out my Dodge real quick.
That sounds good.
Okay. And the point on the given level curve of f. All right, so here's the level curve for f. Compute the slope of the tangent line to the level curve and verify that the tangent line is orthogonal to the gradient. All right, so let's try again. So we're going to look at the curve in the xy plane and find its slope. And then we're going to find the gradient, which is a vector, and we're going to figure out the slope of the gradient, if you will. So over here, our curve in the xy plane, so here's our level curve. So we set the function equal to 1 over root 2 to our upper ellipsoid thing. Oh, here they stacked them.
Yeah.
Okay, so square both sides and do some adding and subtracting. So we get 1/2 equals this. X squared over 4 plus y squared over 16 equals 1/2.
Can you go back up just a little bit?
Sure. All right, so there's level curve. That's a curve in the xy plane.
Multiply everything by 2.
Multiply everything by 2 to put it in standard form. So standard form of an ellipse, that would be x squared over 2 plus y squared over 8 equals 1. So standard form of an ellipse right there, that's the curve we're looking at. Now, we've got to find dy dx for that level curve, for that curve. So, first question is what should we choose for capital F? What do you want capital F to be? So we can do our f sub x over f sub y.
Are you talking about that?
Yeah.
Squared over 2 plus y squared.
Okay, so you want it to be this, like that?
Yeah.
All right, so then dy dx is going to be negative f sub x over f sub y. So negative, and then f sub x is just x. F sub y is y divided by 4. So we get negative 4x divided by y.
That's y divided by 4, right?
Yes,
Okay.
y divided by 4.
Just making sure.
And then we want it at, what was our point of interest? 1, 2. So then dy dx at the point 1, 2, or p, we're going to get negative 4 divided by 2, so negative 2.
So that square root, the big square root is our gradient, correct?
The square root right this
Yeah, that big one, 1 minus.
right here,
Yeah, yeah,
that is our surface.
that's our surface.
Yeah, we haven't taken the gradient yet. The gradient, when we go to take it, which we can do right now if we want, del f is going to be the partial of the big square root with respect to x. We need more space. Let's move this over here. So the gradient, we have to do that thing to the 1/2. So we're going to do 1/2 times the square root. So it's going to put a square root in the denominator. And then in the numerator, we're partialing with respect to x, so we get negative 2x. But that 2 cancels with the half that comes down below, like we've seen kind of very frequently. If we have the square root of x, the derivative of it is 1 over, let's make it square root of 2x. Then it's 1/2 times the square root of 2x multiplied by 2, and the 2's cancel. That kind of thing.
Wait, don't you end up with 4 on the bottom actually?
Over here,
Yeah.
I don't think so, because it's 1/2 the base raised to the negative 1/2 times the, oh, I forgot about that 4.
Yeah.
That 4, sorry, thank you. So we have this quantity raised, so think of it like that, to the 1/2. So it's going to be 1/2, let's put it all in then. So it's 1/2 quantity raised to the negative 1/2 multiplied by the derivative of the inside. The derivative of the inside is minus, it's not just minus 2x, it's minus 2x over 4. Minus 2x over 4. So there is going to be an extra 4 in the denominator. And then we partially differentiate with respect to y, so we're going to get that same square root business downstairs. But we're going to multiply by negative, oh, why did I put it 8? So it's already multiplying by 2. 16. So then we multiply by minus 2y over 16, so it's minus y over 8. So that's our gradient. Let's simplify it a little bit. So here is our simplified gradient. Yikes. There it is. All right, there's our gradient. Ooh. So the gradient is also a vector in two-dimensional space down in the domain. Now we want the gradient evaluated at P. So the gradient at P, which is 1, 2. All right, let's see if we can plug in this correctly. All right, inside the square root, we have 1 minus a quarter minus a quarter. So it's 1 minus a half, so it's the square root of 1/2. Okay, that's the square root of 1/2. Over here, minus y means minus 2, and we should have 16 times. Again, if we plug it in there, we have minus a quarter, so it's 1 minus a half. 1 minus a half is a half, so we have 1 over root 2. So our gradient is going to be negative root 2 over 4, comma, negative root 2 over 8. The gradient at 1, 2. The slope of the gradient at 1, 2 is y divided by x. Y divided by x, does that give us 1/2? So certainly it's positive. So we do root 2 over 8 multiplied by 4 over root 2, and that gives us 1/2. So that's the slope of the gradient. This is the slope of the tangent line.
Okay,
The product of the slopes should be -1.
okay.
All right, all is good.
Why
All
should
is
it be
good.
-1 again?
So 1/2 times -2 is -1.
Algebra.
What does the M stand for?
Slope.
Like
Oh,
MX
slope.
plus
I forgot
Slope.
about that.
Slope.
My old friend.
Your old friend slope. So this says, let me write it here, I'll slide back up in a second. So this is slope of gradient. And this is slope of tangent line. And the product of them is -1. So the slope of the gradient multiplied by the slope of the tangent line is -1. Whew. Seems like taking the gradient is a pain in the neck. Seems like we should go this way. And if we want the slope of the gradient, just flip it and change the sign.
Can we do that?
Yeah.
I feel like you're gonna give us a sneaky trick on how to do gradient next.
Yeah, well, that's one way. At least if we want to find the slope of the gradient.
Right, but if we wanted to find a gradient.
The actual gradient? Is there a trick to the actual gradient? That we'll see. All right, path of steepest descent. This is going to be a hard problem. Let's go to the next problem first, because I don't think you can take that one right
This
now.
is the last one.
This is the last one. This one is more straightforward. That one, we can do that on Wednesday.
No.
Wednesday. I'm getting better. I know. So the only difference here. So this is a real straightforward one. It says compute the gradient. So part A is compute the gradient. So notice that it's a function of 3 variables. Gradient, function of 3 variables, no problem. And because I like you guys, I'll give you a way to think about the gradient for this function.
Aw, shucks.
Oh, shut up.
So, and the gradient evaluated at p. Can anyone think of an application here? So we have a function of 3 variables. This function of 3 variables. The gradient is, so if it's a function of 3 variables, we can't even see the surface, right? It's a hypersurface. The domain is 3-dimensional space. So the gradient is living in 3-dimensional space. It's pointing in the direction of maximum increase in 3-dimensional space. Because what's that? The surface is in the 4th dimension. We can't see it. The domain is in 3 dimensions, and the gradient is in 3 dimensions, pointing in the direction of maximum increase. So this is a temperature function, right? Temperature function, it gives us a temperature at every point in 3-dimensional space. The gradient is pointing in the direction of maximum temperature increase. So this could be used if you're, if you have like a heat-seeking missile. The missile will go in the direction of maximum temperature increase. Right?
Nice noise.
Yeah,
Nice
exactly.
effect.
Boom. Okay, so there's the gradient. Pretty simple. Find the unit vector in the direction of maximum increase. So the unit vector in the direction of maximum increase, so we'll just call it Umax. All we have to do is divide this vector by its length. So 12 over the square root of 145 minus 1 over the square root of 145. So that's our unit vector in the direction of maximum increase. Find the rate of change in the direction of maximum increase. So the rate of change is What?
145.
Yeah. The max rate of change is the square root of 145. And part D, find the directional derivative in the direction of the given vector. So the directional derivative, we take our gradient. So this is part D. Let's just do it right here. We take our gradient vector, and all we do is dot it with the unit vector. Square root of 145. Sheesh. Trying to write quickly. And it's not working. Square root of 145. We just dot it with 0, 1 over root 2, minus 1 over root 2. So that will be the directional derivative in that direction. Multiply that together, and we get a whole bunch of mess. Or, let's see, so this is going to be 12 divided by the square root of 290 plus 1 divided by the square root of 290. So we get the square root of 290 in the bottom, and we get a 13 in the numerator. So that's the rate of change in the direction. Happy Monday. TGIM. All right, see you all Wednesday. Have fun differentiating.
Oh, I will.
Grant always has fun differentiating.